Welcome to WikiPodcast. Have you ever really stopped to think about what makes your phone screen light up or, why an apple actually falls from a tree?
Or how huge galaxies just hang out there in space.
Exactly. It's not random. It's all governed by these fundamental rules of the universe.
Physics.
Right. This deep dive is an introduction to physics. We're exploring the science that connects the tiniest particles to the, biggest cosmic structures imaginable.
Yeah, we're looking at sources covering what physics is, its history, and also just how much it's woven into everything. It's everywhere.
So our mission is to pull out the really key insights from these sources, help you understand what physics is about, how it developed over time, and crucially, why it matters so much to, everything around you.
From that falling apple to the atoms doing their dance inside, everything.
Okay, let's dig in. How do our sources actually define physics?
Well, they put it pretty clearly. It's the scientific study of matter.
Matter.
It's basic building blocks, the fundamental stuff, and how it moves and behaves through space and time.
And energy and force come into that too.
Yep, those related concepts. Energy and force, it's all connected.
Right, so it's way more than just like gears and levers, though that's in there somewhere.
Oh, yeah. The sources really stress how fundamental it is. It's described as one of the oldest and most foundational sciences.
Underpinning everything else.
Pretty much. Chemistry, astronomy, geology, biology, physics often explains the why behind what those fields observe. It lays down the basic rules.
That's a huge point. It's like the instruction manual for reality.
Mm-hmm. And it's old.
Yeah.
Really old. It grew out of what people used to call natural philosophy over thousands of years.
Let's trace that journey then, because the history really shows how our understanding evolved. It didn't just appear overnight.
Definitely not. Way back before recorded history, people were looking up ancient civilizations.
Like Sumerians, Egyptians?
Exactly. And the Indus Valley folks. Even before 3000 BCE, they had some predictive knowledge about how the stars and planets moved. Early astronomy, basically.
And Western astronomy? That came from Mesopotamia.
Its roots are there, yeah. Later, the Greeks started naming the constellations we still recognize.
Amazing. They were charting things so precisely back then, just observing, looking for patterns.
And around the same time, in ancient Greece, you get thinkers like Thales kicking off natural philosophy.
They were looking for natural causes,
Yeah.
Right? Not just saying the gods did it.
Precisely. That was a massive shift in thinking, trying to explain phenomena using natural reasons.
And some of their early ideas were kind of wild, but sometimes surprisingly close.
Yeah, our sources mention atomism, the idea from Leucippus and Democritus that everything's made of tiny, indivisible bits.
Atoms.
Yeah, atoms. And it took, 2,000 years for science to actually confirm that basic idea experimentally. Incredible foresight.
Seriously ahead of their time. Okay, let's jump forward a bit. 4th century BC, Aristotle, his work on physics was massive.
Hugely influential. It dominated thinking for 2 millennia.
But his approach was different from modern science, wasn't it?
Right. He was brilliant, no doubt. But it was more a mix of observation and logical argument. He didn't really do rigorous experiments to test his ideas.
So his theories, like the 4 elements, air, fire, water, earth.
And their natural places, yeah. Or his idea that heavier things fall faster because they want to get back to Earth more. It sounds logical, kinda.
But it wasn't tested against reality the way we do now, which turned out to be wrong, of course.
Exactly. It's a key lesson from history, isn't it? Logic and observation are crucial, but you have to test your ideas against the world, experimentally.
So Aristotle's framework was dominant, but then after the Western Roman Empire's decline, things shifted. Learning continued elsewhere.
Yeah, learning definitely continued, especially in the Byzantine Empire. And then, significantly, during the Islamic Golden Age, they made huge strides, particularly in optics.
Optics, like how light works.
Mm-hmm. This is where we see another critical step. A figure named Ibn al-Haytham around the 11th century. His book of optics wasn't just theory.
He did experiments.
Yes, real experiments,
Mm-hmm.
like using a pinhole camera, basically to show that light travels in straight lines.
That's okay.
But what's really revolutionary, according to our sources, is that he told his readers to repeat his experiments, to verify them.
Reproducibility. That sounds like the beginnings of the scientific method.
You got it. Moving from just watching to actively testing and verifying, it's a huge leap.
And that naturally leads us towards the scientific revolution, right?
Yeah.
When physics really became its own thing based on experiments in math.
Totally. A period of massive upheaval in thinking.
You had these giants transforming everything. Copernicus saying the sun's the center, not Earth.
Kepler figuring out the mathematical laws for how planets move.
Galileo pointing his telescope up, making observations, challenging old ideas by actually looking and measuring.
And then, boom, Isaac Newton.
The big one.
Yeah, he brought so much together. Laws of motion, universal gravitation, explaining the apple and the moon's orbit with the same rules.
Plus, he co-invented calculus, gave physics this incredibly powerful mathematical toolkit.
These guys really built the foundations of what we now call classical physics.
And that developed further in the 19th century.
Right. Driven partly by the Industrial Revolution, you saw big progress in thermodynamics, heat and energy, and electromagnetism.
So classical physics was doing a great job explaining the everyday world. Machines, heat, electricity, magnetism.
It worked incredibly well for a lot of things, but
Cracks started showing.
towards the end of the 19th century, yeah, experiments started giving results that just didn't fit the classical picture.
Like what kind of things?
Well, weird stuff about light from hot objects, black body radiation, or how shining light on metal could knock electrons off, but only in specific ways, the photoelectric effect.
And they couldn't find that luminiferous ether they thought light traveled through.
Nope. Tried and tried. Nothing. These were big puzzles classical physics just couldn't solve.
Which meant we needed something new.
Exactly. It showed our understanding wasn't complete, especially when you looked at very small things or very fast things or very high energies. And that set the stage for modern physics.
Early 20th century. Enter Planck and Einstein.
The game changers. Max Planck with quantum theory, Albert Einstein with relativity.
So why did modern physics have to happen? Classical mechanics just failed sometimes.
Pretty much. It was great for everyday speeds and sizes, but it broke down. Einstein's relativity fixed classical physics for things moving really fast, close to the speed of light. It showed space and time aren't fixed backdrops, they're relative, connected.
Mind-bending stuff and quantum mechanics.
That dealt with the super small. It showed energy isn't always smooth. It comes in little packets or quanta, and tiny things act weirdly, sometimes like particles, sometimes like waves.
So the distinction, classical versus modern. Classical is pre-20th century, right? Big stuff, slow stuff.
Generally, yeah. Mechanics, thermodynamics, electromagnetism, sound, light as we usually experience it.
And modern is 20th century onwards, dealing with extremes.
Exactly. Relativity for high speeds and strong gravity. Quantum mechanics for the atomic and subatomic world. Atomic physics, nuclear physics, particle physics, all that falls under modern physics.
And they have fundamentally different views of nature.
In some ways, yes. Classical physics often sees nature as smooth, continuous, predictable. Quantum theory reveals a reality at the small scale that's often jumpy, discrete, and involves probabilities.
And relativity just completely changed how we think about space, time, matter, energy.
Absolutely. Compared to the classical view, it was a revolution in fundamental concepts. These weren't just tweaks. They were deep insights into how reality actually works.
So how does physics actually work today? How does it advance?
It relies heavily on the scientific method, that whole process of testing theories against experiments and observations.
Trying to be logical, unbiased, repeatable.
That's the goal. It's this constant back and forth. Theorists build mathematical models, make predictions.
And experimentalists design experiments to test those predictions or just explore and see what they find.
Right. And progress really jumps when an experiment breaks a theory or when a new theory points towards an experiment nobody thought to do before. It's a cycle.
And this cycle lets physics cover this absolutely enormous range of scales.
Immense. The sources mentioned it goes from the tiniest things we know, like quarks and electrons, all the way up to superclusters of galaxies, the largest structures in the universe.
It really is the fundamental science, like you said earlier.
And the core goal underneath it all is kind of beautiful, really. It's about describing all this complexity in simpler terms, connecting the dots.
Finding the root causes.
Yeah, and ultimately trying to unify things. Like how magnetism and electricity were found to be two sides of the same coin, electromagnetism.
And the electroweak theory later unified that with the weak nuclear force.
Exactly. And the big dream now is still that theory of everything, one single framework to explain all the fundamental forces and particles, a huge ongoing quest.
Which leads us to the big question for everyone listening. Why should you care? How does all this abstract stuff matter in your daily life?
Well, the simple answer is physics is everywhere, literally. Our sources point to the screen you're using right now, the air you breathe, the stars you might see tonight.
But it's more direct than just being there.
Oh, absolutely.
Yeah.
That abstract world of formulas and forces is what powers the real world. It leads directly to inventions, technologies, the whole modern society we live in.
Okay, give me some examples.
Think about it. Understanding electromagnetism. That gave us radio, TV, computers, smartphones, all communication tech, basically.
Right. Can't imagine life without that.
Understanding thermodynamics, heat, and energy, that drove the entire Industrial Revolution. Machines, power plants.
Even calculus was partly inspired by physics problems.
Yeah, the need to describe motion and change mathematically spurred its development. And think about applied physics today. MRI machines in hospitals,
Physics.
transistors, the tiny switches in every electronic device.
Physics again?
It's fundamental in engineering, too. Designing bridges that stand up, concert halls that sound good, cameras, telescopes.
Makes sense. And things like flight simulators, video games, realistic movie effects.
All rely heavily on physics principles to simulate reality convincingly. Even forensic science uses physics.
And because the laws seem to be universal, we can model things, like how planets form, or test new tech in simulations.
Exactly. That universality lets us understand the past, predict the future, and speed up innovation by simulating things before we build them. It even pops up in unexpected places, like trying to model economies or social behavior using physics ideas.
Wow. Okay, so it's pretty deeply woven into, well, everything, our whole way of life. But it's not like physics has figured everything out, is it?
Not even close. It's still very much a work in progress. There are huge unsolved mysteries.
Like what?
Things like high-temperature superconductivity, why certain materials conduct electricity perfectly at relatively high temperatures. We don't fully get it. And then the big cosmic puzzles, dark matter and dark energy.
The stuff that seems to make up most of the universe, but we can't see it directly?
Exactly. We see its effects, its gravity, but we don't know what it is. And even seemingly simple things like turbulence, the chaotic way water flows, or air swirls.
That's unsolved.
Fully understanding and predicting turbulence is incredibly hard. Richard Feynman famously called it maybe the most important unsolved problem of classical physics. Still tricky.
So physics is definitely not a closed book. It's still evolving, still exploring.
Absolutely. It's a living science, constantly pushing against the edges of what we know, trying to understand reality just a little bit better.
So here's something to think about. Consider that immense-scale physics covers from quarks smaller than atoms to the whole universe, and realize that those fundamental rules it uncovers are literally what allow you to exist and interact with the world.
Every single day, turning on a light, walking down the street, using your phone. It's all physics in action, often completely unnoticed.
Maybe the next time you use a gadget or see something fall or just feel the sun on your face, you might pause and think about the incredible physics making it all happen.
Definitely something to ponder.
Thanks for listening. Write us your opinion in the comments on how has physics impacted your daily life in ways you hadn't considered before this deep dive. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.